In this video, we're going to talk about the properties of gases. So first, let's start with a solid. Take a solid and we add heat to it. The particles of the solid are going to start gaining kinetic energy. That kinetic energy is going to make them vibrate in position faster and more violently. Eventually, those vibrations are going to become so strong that they're going to overcome the intermolecular forces of attraction that are holding it together in this crystalline solid. The particles are going to start to have the property of flow. They're going to start to slip and slide past one another, and that's when it melts into a liquid. If we keep the heat going, though, we're going to keep adding kinetic energy to those particles of liquid. Now they're flowing, they're moving past one another, but they're still connected to one another because of the intermolecular forces of attraction. If we add enough kinetic energy to overcome the attraction that's holding them together as a liquid, that liquid will vaporize into a gas. Now, gases have a property called compressibility. There's a lot of space in between these individual gas particles here. And if I add pressure to this gas, I can push them closer together. And we call that property, the ability to do that, change the volume with pressure, compressibility. So this is the idea behind airbags. Let's watch this video. As the crash test dummy hits the airbag, he starts to compress the gases in the airbag, preventing his face from hitting the steering wheel. The steering wheel is solid. It has no compressibility. So if you're going to hit something, you're going to want to hit a bag filled with gas because your force of collision is going to be slowed down through decreasing the distance between those gas particles in that airbag there. Gases also make good insulators. This is why double pane and even triple pane windows are a thing. So if you have a triple pane window here, it means you have a pane of glass and then a space in between another pane of glass and then even another space. And these spaces are filled with gases. And these gases insulate the air from either side. It can keep cold air out and it can keep hot air in. Same deal with parka jackets. So this is like the most expensive jacket you can buy. This jacket is like well over $1,000 and it has down feathers in it, I believe, some kind of goose feathers. And the reason it's puffy like this is because there's lots of air, there's lots of space between the feathers, and that makes it a really good insulator and makes it really warm in the cold winter. Next, let's talk about variables that we can use to describe a gas. First one is pressure. We abbreviate that with the unit P, the letter P, and the units that we use for pressure in chemistry are often the kilopascal. Next we have volume. We abbreviate that variable with the capital V, and that's typically measured in liters if we're dealing with gases. Next is temperature. We abbreviate that with a capital T, and in this chapter it's very important that we use the unit Kelvin. So we've talked about Kelvin in other chapters. Kelvin is based on absolute zero, and the idea is that we can never have a negative number in the Kelvin scale. So unfortunately, a lot of the math that we'll be doing this chapter, they won't give you Kelvin. You need to convert a Celsius degree into Kelvin in order to do the math problem. And the last variable is amount. We abbreviate that with the lowercase letter n, and we measure amount in chemistry in moles. So these last three, volume, temperature, and amount, can affect pressure, and I'm going to show you how. So the first one is amount of gas. Pressure and the number of particles, or the amount of molecules, are directly related to one another. More molecules means more collisions, and fewer molecules would mean fewer collisions. So the more collisions you have, the higher the pressure is. The less collisions you have, the lower the pressure. Think of a balloon. If you add more particles of a gas to a balloon by blowing it up, you're going to create more pressure, and the balloon is going to get bigger. If you let air out, you're going to have less collisions and less pressure, and the balloon is going to get smaller. So gases are going to naturally move from areas of high pressure to low pressure because there's empty space to move into. Think of a spray can. The reason the paint comes out of a spray paint can is because the can contains the paint with gases under very high pressure. And if you push down on the top, you're opening up the valve so that the gas has a place to move out. It moves from the higher pressure can out to the uh, outside where whatever you're painting. Our next variable is volume of a gas. In a smaller container, the molecules have less room to move, and the particles hit the sides of the container more often and create more pressure. As the volume decreases, pressure increases. So in this diagram on the right here, we're starting off with high volume. There's a lot of space here, and there's low pressure. The particles are rather spaced out, and there's plenty of space to move. But as I increase the pressure or decrease the volume I push down, I now have low volume. There's not a lot of space to move, so the particles of the gas are moving quite rapidly in this smaller space, hitting the container, hitting the sides, creating higher pressure. So as volume decreases, pressure increases. So volume and pressure are what we call inversely related to one another. As one goes up, the other goes down. Our next variable is temperature of the gas. If we raise the temperature of a gas, that increases the pressure if the volume is held constant. Temperature and pressure are directly related to one another. So as one goes up, the other goes up. As one goes down, the other goes down. If they're going up, the molecules are going to hit the walls harder and more frequently if you add more temperature. And this is why you shouldn't have compressed gases in flammable situations here. So in this next video, we're going to show you what happens when one of these tankers containing flammable gas catches fire.
When a tank is exposed to sustained heat, such as from a fire, the liquid within the tank is forced to boil or vaporize, resulting in increased pressure in the tank. To prevent overstressing the tank, the relief device activates, venting the excess pressure. As pressure decreases in the tank, the valve begins to close. With continued heating, pressure again builds, causing the relief valve to reopen. Where flames impinge on the tank below the liquid level, the liquid absorbs the heat, allowing the tank metal to remain at a safe temperature. With continued relief valve operation, the liquid level drops, exposing a greater area of the tank to the effects of heating. With the flames impinging on the vapor space of the tank, the temperature of the tank metal, uncooled by liquid, rises. At some point, due to the vapor pressure from within, the tank metal begins to weaken, stretch, and eventually tear. As the tank comes apart, large quantities of both liquid and vapor are released in a powerful explosion. The heat radiated is sufficient to ignite combustibles and cause burns great distances from the explosion. Tank sections containing rapidly igniting fuel can become flying missiles, traveling great distances, causing secondary fires and other damage. It all happens quickly and with little warning.
Pretty cool, huh? Don't try it at home. So in summary here, you need to know how amount, volume, and temperature can affect the pressure. If amount of gas particles go up, pressure goes up. That's a direct relationship. In volume, as volume goes up, pressure goes down because the gas has places to move into. As volume goes down, pressure goes up because they don't have places to move and there'll be more and frequent collisions. This is an indirect relationship. Temperature and pressure also have a direct relationship. As the temperature goes up, pressure goes up because the particles of the gas are moving faster, so the forces of collision are greater and more frequently. And like in the tanker, it can lead to a dangerous explosion. That is another direct relationship. So you need to know these three. But remember, this is only qualitative. You need to be able to describe these qualitatively, but you also need to be able to express these quantitatively. That means numbers. So we're going to be using these values numerically in the next couple of videos. We're going to talk about some of the formulas that we use to predict and describe gas behavior.